Hi, everyone. Welcome back to E54. Today we'll be going over lecture 7. So our primary focus today is going to stay on mechanical behavior. And we introduced it in our last class, but we primarily focused on elasticity. So we're going to really focus on this plastic regime. So what's actually happening inside of our material and how we can actually change our material to alter that strength of your material. Right? And just a reminder, we talked a lot about bond stretching in the elastic property regime. And in this range, we're really moving on to talking about bond breaking. And the way that's going to happen is that those dislocations that we introduced are going to move around inside of our sample. So we'll talk about why dislocations are primarily observed in metals and alloys. We'll talk about how dislocation motion is related to strength. We'll also introduce some ideas about how, if we have a given material, how could we increase its strength? And finally, we'll talk about things like how heating and processing your material changes strength and how strength correlates with other properties. So let's go back and remind ourselves what an edge dislocation is. This is the simplest type of line defect that we talked about a few lectures ago. We mentioned how we could take our perfect lattice and cut it and add an extra half plane. That's shown right here and also denoted by that inverted T type of sign right there, okay? And that this dislocation could move to the right progressively and eventually give us 1 unit step of slip that occurs inside the crystal. So our crystal is now perfect, but the crystal has slipped and permanently deformed by 1 atomic spacing, okay? And for this edge dislocation, the Burgers vector is perpendicular to the dislocation line. So the dislocation line is going into the board here. Now, that plastic deformation we mentioned is really the direct result of those dislocation motions. So on the top in part A, here it's showing edge dislocations moving. And the end result is we take a perfect cube and we've shifted the top with respect to the bottom. Okay, we can actually do the same thing with the screw dislocation. The screw dislocation line is going the direction my cursor is pointing. And as we shear that, it's going to move back into the left. But the net or end effect is going to be the same. That box of material has shifted and sheared with respect to its original shape. So to understand how and where these dislocations move, we need to think a little bit about what's happening. So we mentioned that we're going to have a permanent step that is 1 atomic spacing. It turns out that we can think and describe the crystallographic systems where these dislocations move. And we can think about the plane on which they move and also the directions. Now, it turns out that these are the 2 choices, the choice of direction, choice of plane, with the highest densities, okay? So if we want to think about that, let's look quickly at this FCC crystal. So we mentioned that the close packed planes were the 111 plane. That's where the atoms are touching along the lines of these triangles. Okay. This picture on the right is showing the sort of atoms at full size. You can see again that they're touching there. So those directions along which they're touching are going to be our closest, our sort of highest linear densities, and those are going to be our slip directions. And then that plane that we're seeing here, that 111 plane, is going to be our slip plane. So for this example of face-centered cubic, our slip plane is the 111 type plane, and our slip directions are the 110 type directions. And if we think about all the options we would have 12 independent slip systems in face-centered cubic. So in some of the other materials, we talked about things like body-centered cubic and hexagonal close packed. The slip systems are similar. They're going to be on the closest packed directions and on the closest packed planes, but there will be some other options too. So quickly, I want to show you this table showing the different slip directions in these different crystal structures. Now, what you'll see here is this is just showing, again, the FCC crystal structures. Here we said there were 12, those 111 planes and those 110 type directions. you can find, again, the directions and the plane along which the atoms are touching. And this plot also, or this table also has common examples of these materials. One thing I want to point out is that both body-centered cubic and face-centered cubic have 12 independent slip systems, whereas the hexagonal close packed, it can only slip along different directions on that basal plane. So that's that close packed plane at the top or the bottom of this hexagonal structure. Now, the point of that is that there's not enough slip systems to have a random type of plastic deformation. And later on in the class, I'll mention a different mode, different way, besides dislocations, that hexagonal close packed can form. Here we're just showing another view of this. So you can see here, this is for a close packed plane. If you were to choose a different direction on that plane, something that's not the close packed direction, you could still, in theory, talk about having slip between atoms along that direction. But in this case, the slip distance would be very large. And in terms of energetics, it's just energetically unfavorable for that to happen. It would rather happen along these high atomic density directions. And again, those occur different places within these two different crystal structures. These are showing the face-centered cubic and the hexagonal close packed crystal structures. In the hexagonal close packed, it's along the top or the bottom of that hexagon, and it's along these triangular shaped directions and planes inside of the face-centered cubic. So what that means is that since dislocations are moving along certain planes, we often don't just care about the macroscopic force that's applied to our sample. So if I take and I have some tensile sample, I'm going to pull on it, I want to measure that force, but what I really care about is what's the stress on the sample, and not just the tensile stress, but the stress along a certain plane. That's that slip plane where dislocations want to move. So what I really care about is what's called the resolved shear stress. And all you're doing is doing a geometric transformation and thinking about when I apply a force and a stress vertically here, how would I end up getting a shear stress along some given plane with a plane normal, n sub s, and a slip direction shown here. Now, we can just do some geometry and figure out how to connect those things. We can find what's the force in that shear direction, what's the area that's shearing. And both of these are going to introduce a cosine into this equation. And basically what we can see here is that our resolved shear stress we get on this plane is going to be equal to the applied tensile stress in the vertical direction, multiplied by the cosine of these two angles. So what's the angle between the applied force and the shear direction, and the applied force and the normal of that plane? And generally what happens is when that when that resolved shear stress gets above a critical value, that's when we have dislocations moving and our sample plastically deforming. So we can think about how that sort of relates to the orientation of our sample. So if we were to pool on this tensile sample shown here, and the slip plane we were thinking about was perfectly horizontal, we could ask ourselves, what would the resolved shear stress be? Well, one of those angles is 90, so the resolved shear stress is going to be 0. Okay, so in this orientation, we would never have dislocations moving right and left. In contrast, if that plane was at 45 degrees, we could go and calculate what the resolved shear stress would be, and it would be this applied tensile stress divided by 2 along that 45-degree angle. And again, we can find the other extreme of this. If that slip plane was oriented vertically, we would again get 0 resolved shear stress. So these two extremes on the right and left, we would never get plastic flow. The dislocations would never move. In the middle, this would be the easiest time we can get them to move. And that's actually where that observation that we saw when we first introduced dislocations came from. That surface of that sample where we have those slip steps is just those slip planes being visualized after we've had lots of dislocation motion along. This plot is just showing all the different options between those extreme values. So we just showed these three values of 0, 0, and the max. You can actually see that by plotting for a given level of applied stress, what would the resolved shear stress be as we change one of those angles? You can see it goes from 0, increases, reaches a max at 45, and then goes back to 0. Now, the one thing that is a bit odd is I've mentioned that we need to know the angles between these different vectors inside of our sample. And it turns out that you could either ask yourself, well, draw this in space and try to figure out the angles, or you could use some of our linear algebra tools to find those values. And often it's important to remember that when we take the dot product of two vectors, so vector A and vector B, we're going to take the dot product, that's equal to the magnitude of those two vectors times the cosine of the angle between them. So that's one way we can easily find that cosine angle and plug that into a calculation for resolved shear stress. So here's an example. So let's say we're deforming a single crystal. We are taking and we're applying a given stress of 45 megapascals. We know what the slip planes are, so we can tell ahead of time what these angles are. And we have our resolved shear stress as being 20.7 megapascals. So the first question we can ask is, will our single crystal yield? I'll give you a second to think about this, how you would go about running through this problem. All right, so the first thing we want to do is we see what we have in there. We have these angles, we have the applied stress. We want to pull up that example, or that equation that relates all these values. So we have the stress, we have these angles, we can plug it in and find what the resolved shear stress is, and then compare it to that critical value. We plug in these numbers, we'll get that our resolved shear stress is 18.4 megapascals. That's less than that critical value, so our sample will not be yielding in this situation. Okay. Now, since our sample didn't yield, we can go into that second part of that question. So what stress is needed? What applied stress sigma is needed to get the sample to yield? So we can change that sort of analysis a little bit. We're going to keep those angles the same. So our geometry of our sample hasn't changed. But instead, we're going to say, let's enter the critically resolved shear stress on the left side of the equation. And let's solve for what's the value of sigma. So what's the yield stress of the sample in this orientation? We'll flip this around and find that if we apply a stress of 50.5 megapascals, our sample will yield. Now, that was an example of a single crystal, so only one crystal in the whole entire sample. Oftentimes, we'll find real materials are made of polycrystalline materials, but we can still see that same evidence of dislocation slip. So this is a sample which has been polished and etched, so you can see many of the grains. I'm outlining one here. There's another one here. And on the surface of this is a sample that's been heavily deformed. You can end up seeing those slip steps where the dislocations came out. And if you look at these different crystals, you'll see that those lines on the surface are oriented sort of different ways in comparison to how we're looking at it. And all that means is that, so each of these is still going to be that closest packed plane, this closest packed directions, but how that's oriented with respect to our viewing direction is different, okay? So that resolved shear stress in these different grains, when I load it in this tensile orientation, is going to be different. And what that means is that grains are going to start yielding at different values of applied stress. And the grain that is oriented with the largest resolved stress, we said that might be at an angle 45, so it might be this grain right here, is going to be the one that yields first. Now, I mentioned that in hexagonal close packed materials, there's not enough slip systems. So dislocations will move, but if I want to take and deform a material in some sort of arbitrary manner, I can't always rely on dislocations to take over. So I just want to mention that one of the other ways that hexagonal close packed materials can deform is through what's called twinning. And that's a process where we take this perfect crystal and we shift it such that in this case, now there's these two mirror planes inside of my sample. So you're seeing that on the right and left, I run into atoms at the same place of both of these two planes. Okay, so they look like two little mirror planes. That region in the middle is what's called a twin. And you can see that rather than just moving that extra half plane of atoms and having small displacements, this whole section on the right here has shifted and displaced. Okay, so that's one other mechanism that can occur in HCP materials. One thing I want to talk about too is the sort of strength in different directions of a sample. So generally, if we have a polycrystalline material, so there's many, many different grains, if these are equiax, so they're roughly the same dimensions in all different directions, and they're randomly oriented. So they're all different orientations, and there's no sort of preference that they're all oriented, aligned with each other. We pull this material in the vertical direction, the horizontal direction, off at different angles. We'll measure the same yield strength, and we can say that our material is isotropic. Now, that's not always the case. And one place that this can come up is if we do what's called rolling to a material. So if we take a piece of sheet metal and we are pushing it through these rolling features. So these are cylinders that are going to push our material through, and they're also pressing down with some force. And the idea here is that this piece has a smaller thickness once it's gone through this rolling process. But practically what happens is those crystals often get reoriented and changed. So in this case, the grain orientation of their shape has changed. So for example, the grains are longer in this horizontal direction than the vertical after this rolling treatment. And you can actually see some practical effects of this. So this is an example showing if you took a cylinder of tantalum, so this is a BCC metal, you machined it into a plate through that rolling process, and you cut a piece out of it and fired it into a surface. So this is a very hard surface. We're going to fire that into the surface and see how it deforms. And you looked at it, you would find that it does not deform in a uniform manner. So this thing, which was originally a perfect cylinder, it was cut out of that plate. We slammed it into the surface. You can see that where it hit the surface, it deformed. But if you look at that end, you'll see that it deformed more in this horizontal direction versus that vertical direction. Okay, and that's just a result of the fact that the grains and the crystals have been elongated and changed in their orientation. So the next thing we want to talk about is how we can actually change the strength of our material. And there's lots of different methods. 4 of them are listed over here on the left. But the basic idea is that all of these samples shown here, this is a bunch of sort of rough ideas of what your strength of your material might be on the y-axis and your elongation of failures. This would be the ductility. And this is on the bottom right, you're starting from pure copper. If we move up here to the left, this is brass. So this is copper plus some alloying element. We get different strength. So our material becomes stronger and less ductile. In contrast, you can also increase the strength of your material by doing what's called work hardening. That's where you're deforming your material. We'll talk about exactly what that is and what happens. You can do multiple of these things. You can you can alloy your material, add in a second element to make it brass, and then you can work harden that brass and keep increasing your strength. And you can do this and move amongst the space and increase the strength of your material. Now, one thing I want to point out is generally as your strength goes up, your ductility goes down. So the first way we can increase the strength of our material is through what's called grain size strengthening. And the idea here is that if we think about This is showing a slip plane and an edge dislocation that's moving around. It's going to want to move in this crystal, this grain A, because the resolved shear stress is such that it's going to push it to the right. When it comes to a grain boundary, or where another crystal B, butts up against it, there's going to be a change in that slip plane and how it's oriented. Okay, and what that usually means is that we have to apply more macroscopic tensile stress to our sample to get it to push along that new plane. Okay. And generally, if we have a smaller crystal size, that means that as this dislocation moves through our material, it's going to hit more of these grain boundaries. We'll have more barriers to slip. The net result is what's called the Hall-Petch equation. This says that the yield strength of our material is going to be equal to some constant plus, so this is something that's sort of the strength of the material without grain boundaries, plus a constant, K, times the inverse square root. So 1 over the square root of the grain size, D. That might be the width of one of those crystals. So what that means is as the grain size goes down, this term right here on the right is going to become very large. We can also find a way to strengthen our material by thinking about how if we add in second elements, they would interact with that dislocation. So if we look around that material, this is again showing an edge dislocation. So here we've added that extra half plane of atoms. In that region above the dislocation, the atoms are smushed and are closer together than they would like to be. So they're under compression. In the bottom, the atoms to accommodate that are pulled apart a little bit. So they're pulled in tension to accommodate that. Generally, you have this region around the dislocation where you have some distortion of the lattice. Now, if I add other elements into my system, they're going to actually be they're going to be attracted to certain regions around these dislocations. Okay. So we can think about, for example, if we take and add some alloying element. So our original atoms were these white atoms. We add this orange atom in the middle. This atom, in this case, is smaller than the atoms around it. So it is going to sort of pull in and apply tension to all that lattice around it. Because it's smaller, it's actually going to be happy in that region above the edge dislocation where the atoms were originally compressed. So it's basically going to relieve the penalty from having stress around that. You can think about the opposite. If I put in an atom that is normally bigger than the lattice, it would want to push out on all those atoms. So it's actually happy in this region where the atoms are already pulled outwards. Okay, so a larger atom wants to go below the dislocation. We can see this effect with our virtual material science and engineering tool. So let me exit out of my slides real quick. And I will go to that. So again, read, study, practice, MSE. You can look at dislocations. We already did that. We're going to look at what happens when we have solid solution strengthening. So we can see things like videos. So we won't listen to the whole video, but in this case, they're showing the stress fields around the dislocation, and then how they interact with lattice defects, so different defects, and how those defects want to interact and move to be in certain places around that dislocation and relax that strain field. Right? So that's helpful it's a helpful tool for moving around and playing with and understanding those things. So we can actually use this to our advantage, and we can create what are called solid solutions. So we're adding in, we're replacing some of those atoms in a way that are going to interact with the dislocations. So if we have a smaller substitutional impurity, that's going to cause some tension around the lattice. And as a dislocation moves, it's going to be hard to move it past certain points. What I'm showing you here is that the stress that's opposing the dislocation motion is highest at points A and B. So it'll be to the left of the dislocation if the dislocation is above that impurity. It'll be to the right of the dislocation if it's below. But that doesn't really matter. What matters is if you think about this dislocation needs to move long distances in the material, every time it interacts with an impurity, it's going to have to overcome that local obstacle. You can do the same type of calculation for if we have a larger substitutional impurity. All it does is it flips these locations of these places where the impurity is opposing the dislocation. But either way, what we do is we have a barrier to moving the dislocation, which makes it a little bit harder to plastically deform my material. So we can see some data for solid solution strengthening. This is showing a base material of copper, and we're adding nickel. This is a good choice. When we talked about those Hume-Rothery rules, said that this would be a material which has a full solubility range. So we can go from 100% copper to 100% nickel. And what you'll see here, this is plots of where real data lies, of the ultimate tensile strength increasing as the composition goes up, and also the yield strength of the material increasing as the composition goes up. Now, the empirical relation that's used to describe this is trying to recreate the shape of these curves. And it says that the yield strength of my material increases with the concentration of those solutes with a square root type of form, okay? So yield strength is proportional to the square root of the concentration. Okay? We can also have what's called precipitate strengthening. So this is if instead of just replacing out individual atoms, we have fully distinct second phases. And an easy example of thinking about this is if I added ceramic reinforcements. So maybe I added silicon carbide particles to something like iron or aluminum. In this case, as the dislocation is moving along, it actually comes to a full precipitate, and it has to a full second phase, and it has to move past it in some form. There's two ways that that can happen. One that can happen is it can actually cut this precipitate. Okay, and you can think about it as the dislocation's moving, it's displacing that precipitate by one atomic space as well. This tends to happen when that precipitate has the same crystal structure as this material around it. There is another option. So if the dislocation can't cut through that precipitate, that usually happens when it has a different crystal structure, it can bow around. So the dislocation gets stuck near that precipitate, but the part of the line that's away from that particle can keep moving out. And eventually this can sort of shift and advance past that precipitate. The main thing that matters here is that in either case, these mechanisms predict that our yield strength of our material is going to be proportional to 1 over the spacing between those obstacles. So what you really want is those particles to be spaced really close to each other and have lots of obstacles, that dislocation moving. We'll talk about ways of developing these types of microstructures. So don't worry too much about what's in this top left picture of this plot. But this is showing that if we add some solutes to our system, at the beginning, they'll just replace those atoms in a substitutional defect type of way. So here we have some of these red atoms just on the same original lattice. But if we add too much, they'll start to form second phases. So this is showing how eventually we've added enough of these red atoms that it forms the second phase that I've labeled theta. Okay, and this would be a new particle. You can see that the planes of the atoms don't always match up with the planes of the white atoms in either of the directions. So this would be something that has a different crystal structure. We can actually do this in addition by adding more and more of those alloying elements. We can also heat up our material and let this happen. So if I make something where maybe aluminum is my base material and copper are the alloying elements I've added in, and I go and heat this for different amount of times, I'm giving it enough thermal energy so these copper atoms can find each other, cluster, form these second phase particles, and then these particles can grow. And that gives us something like this plot on the bottom. So our strength of our material changes with what's called aging time. So this is the amount of time I'm heating. And our strength increases as we nucleate out those second phase particles. But eventually, if we continue this heating experiment forever, those second phase particles are going to keep growing. And what that means is if they keep getting bigger and there's a limited amount of that copper in the system, in this case, the particles will be bigger but further apart, and then our strength will then go down. Sometimes the beginning part of this curve is called aging, and the latter part where the strength is going down is called overaging. So this is very important in many places, and a good example of that is in the internal wing structure of airplanes. So we make these systems out of aluminum because we want this material to be very light, but we also need it to be strong so that our plane is safe. And what we do is we don't just use pure aluminum, we instead use aluminum that's strengthened by many precipitates. So this is showing, this is 1 grain right here, the aluminum material. There's some precipitates along the grain boundaries, but there's also many these dark spots inside of this region, and those are second phases that have come out inside the material. Finally, we can think about how dislocations interact with each other. So we mentioned that there's compression above and tension below that edge dislocation. And we can think about how if we have 2 dislocations near each other, how would those stress fields interact? So I'm going to put 2 edge dislocations. In both cases, the half plane is pointing up. Above it is compression, and above this one is compression. If I brought these dislocations directly over each other, I would have double the compression. The system doesn't like that, and that's bad. So I'm having higher stresses inside my material. So what happens is when these dislocations get near each other, they actually will feel some sort of repulsion. They'll be pushed away. This one on the right will be pushed to the right, this one on the left will be pushed to the left. Now, I can think about putting 2 dislocations near each other that are of opposite character. So I have an extra half plane going up right here, and I have an extra half plane going down on this dislocation on the right. And what that does is it flips these stress fields. So now the compressive region is on top of the dislocation on the left, and it's on the bottom of the dislocation on the right. Now, if I think about putting those dislocations on top of each other, like is shown here, those stress fields actually cancel each other out. So rather than having compression inside of my sample, compression at negative stress plus tension at positive stress equals 0 stress. So these types of dislocations are actually attracted to each other. And a cool thing can happen. If I put an extra half plane up on top of an extra half plane down, what do I have? I now have a perfect plane. So this is actually what's called dislocation annihilation. If these 2 dislocations come together, there's no longer a defect in my crystal. So this leads to what we can call dislocation or work hardening. And the basic idea is that if I do what's called cold working, so I deform a material and get those dislocations to move around and interact with each other, I can get them to entangle and create some stored network of dislocations inside my material. This is showing a picture using transition electron microscopy of titanium, and all of these black lines are dislocations going through the material. So that's an interesting kind of cool picture, but also think about if I then want to deform this material after this. If a dislocation has to move through here, it's going to have to move past all of these other dislocations, which are now acting as obstacles. So when we talk about this type of mechanism and how these obstacles matter, it's important to be able to put a number on that. So we use something that's called dislocation density. And all this quantity is it's the total dislocation length. So if we added up the length of all that dislocation, all the dislocations in that sample, that would be the top of this ratio. And then the bottom is the unit volume of the material. Okay? So it's basically telling us how much dislocation do we have per unit volume. And what you can see is that this number can vary quite a bit. So even for carefully grown single crystals, you'll still have something like 1,000 dislocations per millimeter squared. But if we deform the sample, that can increase this by many orders of magnitude. So here we're going from power of 3 to the power of 9 or 10. And in contrast, if I take that heavily deformed sample and I heat it, that number can drop back down a little bit. It won't go back to that 10 to the 3, but it might be 10 to the 5 to 10 to the 6. So it can be get big changes. Now, if those dislocations that are inside of our sample are acting as obstacles, if I have more of them, my strength of my material goes up. So the yield strength of your material increases as the dislocation density increases. And it actually has a form that looks like what we saw for composition. So the yield strength of our material is proportional to the square root of the dislocation density. All these equations we've been talking about for strengthening of materials are really talking about adding obstacles to dislocation motion. So if we have my perfect lattice, there's some sort of stress that needs to be overcome to move the dislocation back and forth, but it generally is pretty low. And then whether I'm adding solute atoms, a full second phase, which really has a different crystal structure, or a dislocation that intersects that slip plane, in all of these cases, I'm talking about adding an obstacle, something that makes it harder for that dislocation to move through the lattice and have plastic deformation. And this is just showing as the dislocation moves, it's going to have to get past that obstacle, okay? Those can be small little solutes within my lattice. They can be a big second phase particle, or they can be, this is showing a bunch of dislocations in the vertical direction that this black dislocation has to move past to give me plastic deformation. So as we cold work our material or deform it more and more, we'll add dislocations. We can change the mechanical properties of our material. This is showing a low carbon steel, and these are stress strain curves for something which has not been cold worked at all, so 0% cold work, and then cold worked 4% and 24%. And you can start to see some trends. So as we cold work more and more, the yield strength of that material increases. The tensile strength increases. So remember, that's the maximum strength of the material, the peak of that curve that goes up. And finally, the ductility decreases as we add more and more cold working. Okay, so let's do some sort of sanity checks to make sure we're thinking about this the right way. Grain size reduction will do what to materials? Will it strengthen, weaken, toughen, yield, or embrittle? Well, the major place we talked about grain size mattering is that if we add those grain boundaries, those are going to be obstacles to dislocation motion. So if my grain size gets smaller, I'm going to have more obstacles in my system. So that tells me that I'm going to strengthen my material. Okay? But I'm not trying to trick you. We have to think about whether or not any of these other ones are true. And we did learn that as our material gets stronger, it loses its ductility or it becomes more brittle. So actually, there would be two answers to this. It would be A and E. All right, let's do another one. So if our material is cold worked, so it's plastically deformed, what would we think would happen to our yield strength? Okay, when we cold work, we're adding more and more dislocations into the sample. These are going to be obstacles. We mentioned obstacles increase our strength. The answer is it will increase our yield strength of our material. All right, if a material is cold worked, we just said our yield strength goes up. What do we expect to happen to ductility? We said that strength and ductility are usually inversely related. So generally our ductility will decrease. Okay, so let's look a little bit more at these property alterations after cold work. And one of the things we need to talk about is how we can describe that cold working. So if we think about having an original cylinder that starts at 15.2 millimeters diameter, and what we're going to do is we're going to take and we're going to cold work this to form it, pull on that until the diameter is reduced to 12.2 millimeters. This is actually a good example because this is what happens when you do what's called drawing copper wire. So you pull it so that it becomes thinner. You can put a number on that by describing what's the change in the cross-sectional area of that wire. In this case, we can cancel out all those pi over 4s, so that we just describe it in terms of what the diameter is. So in this case, if I plug in some numbers, I'll talk about the decrease in my diameter divided by the original number. I'll see that it's decreased by 35, the area is decreased by 35.6%. So we can then go and look up some literature values. So we can go and find what's the yield strength, tensile strength, and ductility of copper as a function of that percent cold work. And since we calculated what that is for this case, we can go and read off the values. So our yield strength will be about 300 megapascals. Our ultimate tensile strength will be about 340 megapascals. And our ductility will be about 7%, okay? And again, we can see those trends that we talked about. Yield strength and tensile strength go up, ductility drops as cold work goes on. Now, we also mentioned that heat treatments or annealing our sample can matter. So if we take a material that's been deformed and we heat it up, we can also observe that that will change the properties of the material. So if I take and I heat a material, and this is showing data for 1 hour treatments at each of these different annealing temperatures. As I increase the annealing temperature, my tensile strength will fall, but my ductility will increase. Okay, and that again is aligning with this idea that these are inversely related. But what's important is we can talk about what's happening inside of the material in each of these different ranges. So the first thing that happens is something called recovery. The next is something called recrystallization, and then finally grain growth. Now let's work through each one of those. So in recovery, what's happening is our strength slowly starts to decrease because we're reducing the dislocation density. So we're giving the sample some time and temperature, and we're letting the number of dislocations decrease. One of the ways that this can happen is through diffusion. So if you think about, we mentioned if we have an extra half plane of atoms right on top of a extra half plane of atoms pointing down, these things can annihilate and there's no longer a defect. Sometimes these dislocations can be over top of each other, but they're not at the same vertical location, okay? Well, one way that these dislocations can annihilate and go away is that atoms can diffuse to these regions which are under tension underneath of them, okay? If I think of 4 atoms filling in that empty space, I now have a perfect plane of atoms. This is just showing that. You can also think about how dislocations can overcome obstacles. So in this case, I'm trying to move this blue dislocation through my sample. There's some obstacle that's red. I'm drawing it as a different dislocation. Let's just say it can't get past that obstacle. That sort of diffusion can allow this dislocation to get over and past that obstacle and now move. And if this continues on, maybe that dislocation can move outside of the sample, can move to a surface. Now there's one less dislocation inside of my material. Or it can meet another type of dislocation of opposite character and annihilate. That's called recovery. So the next step is what's called recrystallization. So this is showing optical micrographs of that. So on the surface, you see all these slip steps. You see a big grain right here, and inside of it, there's all these slip steps from dislocations moving around. If we start to heat it up and give it some time, we would start to see these little dark regions inside of all of those heavily deformed grains. These are actually new crystals that are nucleating and growing inside of those heavily deformed grains. What's actually happening here is all of those dislocations that are inside of the grains are defects. The system doesn't like it. It pays some energy penalty for having those there. So it wants to get rid of them. Now, we talked about recovery. One way it can get rid of dislocations is by moving them out of the crystal or finding other opposite character dislocations. But another option is a new grain with no defects in it can actually nucleate and grow. And that's what's happening here. All of those dislocation, or all of those heavily deformed regions are nucleating new dislocations. You can actually see the grains that are nucleating are coming along some of those slip planes. Those grains start to encompass all of that heavily deformed area, and by some time, we no longer have those large, heavily deformed grains. We instead have small, tiny little crystals. So these new grains are formed where we have originally had high dislocation density, but now they are new and perfect, so they have low dislocation densities. They're generally pretty small in size, and they're going to consume and replace those cold worked parent grains. And eventually they'll fully take over and replace those. Now, at some point, we'll have these new recrystallized grains. If we keep giving the sample time and temperature, those grain boundaries, which again are defects, can keep moving. Those grains can keep growing to try to get rid of those defects. So we can think about that new recrystallized grain to keep growing and maybe get rid of a smaller grain here. Generally, that process of grain growth, so the grain size at any time to the power of n minus the original grain size to the power of n, follows some law that's kt, okay? So this is called a power law for grain growth. So at longer times, the average grain size keeps increasing. The small grains are shrinking, and they're ultimately going to disappear, and the large grains grow. So if I look at that fully recrystallized sample after 8 seconds, if I let that process keep going on, maybe give it 15 minutes, I now see that I have these big crystals here. These are these small ones that are growing until they're big, okay? Now, in that type of process, I'm removing those grain boundaries, and I have fewer obstacles to dislocation motion. And this is just putting some labels on those features. So the grains at a given time, the original grain size, some coefficient that depends on material and temperature and the time. And this is showing you that sometimes or usually for regular metals, that exponent will be something like 2. So when we're seeing this type of behavior where the tensile strength drops and the ductility goes up, we can actually correlate that with the grain size and the microstructure at any of these times. So originally we have these big, heavily deformed grains. We start to have recrystallization at some critical temperature called the recrystallization temperature. Those begin to take over and eat those heavily deformed parent grains, and eventually the whole material, and then eventually those coarsen. Now that recrystallization temperature is going to be different for different materials. We can define it as the temperature where this recrystallization process finishes after 1 hour. Now this depends on your material, but for most materials, it can be found in some given range of the melting temperature of that material. And it's usually between 30 and 60% of the melting temperature of the material. Okay. For a specific alloy or metal, the reason we would have variations in this range between 30 and 60% is that it depends on the percent cold working. So you can imagine if I have a heavily cold worked material, there's a lot of dislocations in the grains. That means there's a large driving force for this recrystallization to happen. It's going to be very easy. It might be towards the bottom end of this range. And generally that recrystallization temperature decreases with increasing cold work. It also depends on the purity of your metal. So as purity increases, that recrystallization temperature decreases as well. So a very pure metal is easier to crystallize than one that is sort of dirty and heavily doped. And finally, there's some other terms. We talked about working a material, and it turns out that when I said cold working, I was sort of referring to being below this recrystallization temperature. So if that's the temperature when the system can get rid of all those dislocations I'm putting in, cold working is what happens when we deform our material below that. So in this case, it can't recrystallize, and I'm adding lots of dislocations to the system. In contrast, if I am heating the sample and trying to deform it above that temperature, I'm not going to be adding many defects to the crystal because that recrystallization can sort of reset the microstructure whenever it wants. Okay? These are actually used for very different reasons. Usually we cold work a material to make it stronger. We hot work it to change its shape. A good example is if you've ever seen the movie or worked in a sort of blacksmithing type of class, you'll see that somebody's taking something, maybe like a sword if it's in a movie, and they're hitting it with a hammer. There's really two different times they're hitting it with that hammer. Sometimes they put that sword into a hot furnace and it's glowing bright orange, and then they're hitting it. When they're doing that, they're hot working their material. They're trying to change the shape. Then when it cools down, it's no longer glowing red. If they keep hitting it, at that point, they're cold working their material. They're trying to deform it so they can change its properties. So this grain size that we see in our material is going to influence our properties. Metals that have small grains are relatively strong and tough at low temperatures. So that means it's hard to deform. And in contrast, metals that have large grains are easy to deform into the shape you want and very ductile. So you can think about it in an analogous way to that cold and hot working. So if I have really small grains, my material might be hard to deform. And if I want a strong bridge, that's what I want. But on the other hand, if I want to take some piece of sheet metal and form it into a shape so that I can make a car out of it, I might want my metal to have large grains. So it's important to think about how these different features of your microstructure are affecting your properties depending on the goal you have in mind. So just to summarize, so dislocations are what we see inside of metals and alloys, and these are what carry and cause that plastic deformation inside of these materials. If we want to increase the strength, we want to make it harder for plastic deformation to happen, and we do that by making it hard for dislocations to move. What we generally want to do is we want to put in obstacles to dislocations. We can do that by decreasing grain size, adding alloying elements, so we either have solid solution strengthening or precipitate hardening, or we can beat up our material, add dislocations themselves, which can serve as obstacles through what's called cold working. Okay. Now, once we heat up that cold worked material, we can have these different processes of recovery and crystallization and grain growth happen. All right, so that brings us to the end of today. Thanks for your attention, and I will see you all in a Q&A session soon.